Let's take a look at section 20-1. Okay, so we're going to begin we're going to do a lab next week on this. You guys have Zelda next week. I'm going to try a new lab with you guys this year, so it's going to be a little experimental, so you're going to have to bear with me. We'll see how it goes. Because we're going to do something with a little apparatus I have the following week, but this one is it's kind of cool. It's called paper circuits. So there's this ink that is conductive ink, so you can literally draw a circuit and it acts as a wire. It's kind of cool. Like the ink itself is metallic and it has these ions in it, these electrolytes, I guess, ions probably, particles that make the actual ink metallic. And you can actually hook up like a light bulb to an actual piece of paper because the metallic surface of the paper. But you have to use like glossy paper and stuff, like the photo paper. Yeah. So I have all of this stuff. We're going to try that. In addition to that, I bought this, it's a roll of really thin metallic tape. Like you would use double-sided foam tape, that thick tape that exists now by 3M, not Scotch tape. It's got like a backing to it, you peel the backing off. This stuff is this thin metallic tape, you peel the backing off, and you could use that on paper as well. So I want to see which one works better. So it's going to be very experimental what we do next week. I haven't had a chance to try it yet. Hopefully I'll be able to try it before we do it. But I want to try that and come up with our own simple circuits. And then when we get to section 20-2 and 20-3, we'll look at parallel and series circuits and see the differences, and we'll do a more complex lab where I have a little circuit board for you to work on. Okay, but this one we'll try next week. It'll be something new. So we're going to look at schematics first. What's a schematic? What's a schematic? What do you think of when you hear the word schematic? Contraction, okay. Scheme, the word scheme, schematic, that does not that relation, but some other relation. A blueprint, that's a good way of putting it. You said design, right? Yeah. Schematic, think of design, blueprint. Okay, those two words are pretty interchangeable with schematic, that works. So we're going to look at schematics. We're going to talk about open and closed circuits, which we've already mentioned. We're going to talk about potential difference, which we've already mentioned. A lot of these things we've alluded to, but now we're going to see them in circuits. And then we're going to look at the study of the workings of a light bulb. I find that actually be the most interesting part of this. Okay, to actually see what happens in a light bulb. With this one first. Recall this information. Actually, I have my notes in the next room with little tidbits I want to add. Pablo, can you read, please? I want you guys, while he's reading, to follow along the diagram to remind yourself of what we spoke about yesterday with this diagram.
Add the battery terminal for the potential energy.
Why are you so awkward when it's there for you? Continue reading.
And when it moves from B to C, the energy is converted into the internal energy. When then the current warms up, when the charge returns to point D, the battery then goes from point D to A. The charge increases the potential energy by the same amount of potential energy lost by battery.
Okay, so this is what we talked about, that schematic yesterday, the idea of what's going on here. So just to recall that information first. I didn't ask you, but do you have your labs for me, people?
CC.
I didn't ask it, so I was hoping you just had it in. Why missing it? Let's figure out.
Oh, yeah, sorry about that.
Wait, I don't know mine.
Monday.
Okay.
Well, you gotta get it quicker so you're on time for that.
Okay, I have it downstairs.
I'm gonna be right after this one.
I also have it.
Okay. Oh, shoot. Did, Constance, I have yours already, right?
Yeah.
Did, Alejandro leave his with anyone?
He would have left it with me.
Did he? No.
But
I have.
That means no.
I think I have my folder
I'll talk to him.
downstairs with it.
Get it for me right after school, Frank.
Okay.
Just run it back up. All right. The schematic we're going to take a look at is, again, a blueprint, as Theo said, or as Ann said, a diagram. And that's physically what you're seeing here. So if I have a battery, and I attach a wire to it, and then run that through bulb, another wire to another bulb, and then another wire back to the battery. That's physically what you're seeing in this diagram. It's a representation. So anything that uses energy, anything that draws power, the rate at which energy is used, is considered a resistor. Now, bulbs specifically have a different symbol, but this is a general symbol over here. So the battery is your power source. That's shown by a longer and shorter line indicating a positive and a negative terminal. These are considered to be what are called resistors. Let's quickly look now, though, at specific symbols that we can use in this section. So the first thing we're going to look at is a wire. Okay, wires obviously are conductors. We know that wires have very little resistance, almost negligible, so we don't write them as resistors. Whereas resistors themselves have a lot more resistance than a wire. So the wire is simply drawn with a line. Anytime you have a wire, use a line. Usually with schematics, you draw schematics at right angles. Does that make sense? Right angles? So it's written like a box. You wouldn't draw a circle with the line. You would show the wire going like that, even if the wire doesn't actually do that. So if I hooked up look at that last diagram again. Let me pause and go back. Resistor, also known as a circuit load, meaning it can take the energy from the power source in the circuit load bearing element. A resistor is drawn with a squiggly line. Why might that be? Why might there be a squiggly line? What is that showing you? Exactly. The charge carriers are bouncing around that resistor, which is slowing it down. Very good, Bob. Okay, that's the squiggly line right here for the resistor. Now, a bulb is a resistor, really, except it's drawn with a circle around it. I draw bulbs like this. When I was in high school, I learned it this way. It doesn't matter, though. And then I put a circle around it like that afterward. So I just draw a resistor. See the blue there? I just draw a resistor and then I put a circle around it and indicates a bulb. A light source is one of your standard resistors, so they kind of came up with another symbol for it, even though it is still a resistor. A plug is not widely seen, honestly, in circuits. We use batteries in class, but if you were looking at a circuit diagram of something like a classroom, obviously, you have plugs everywhere. Okay, so a plug looks like a plug. I would choose this for a plug. I would not use this. That does not seem reasonable to me. Okay, just like I wouldn't use this one either. So for a plug, I would use a circle with two different length lines. The longer line is the positive terminal. The shorter line is the negative terminal. Okay, you're going to see that in a moment with the battery. Okay, the battery is just, again, shown right here. Okay, here's the battery. The longer line for the positive terminal, the shorter for the negative. Very similar to the plug. Look at the battery and the plug. Okay, the plug has a circle around it, the battery doesn't. That's the difference. Multiple cells in a battery are drawn like that on the bottom right. So if I have a laptop battery, it's usually a 6-cell battery. So in the diagram, you would literally see the battery with 6 of these arrangements. That's a 3-cell battery right there. What else? A switch. This is what a switch physically looks like, just so you know. You hook up your wires. Let me point on the diagram, actually. You hook up your wires here and here. At some point on the bottom, there's a metal contact you may clip it into. If there's a wire here, and then another wire coming out of here, and then these are connected to like a bulb and a battery, with this open, no flow is continuing through the wire. As soon as you close this, the wire, watch, goes through one, through the metal, out the other end of the wire. But here, look, it can't go anywhere. There's nowhere to go. This is air. It can't cross air on its own. So this is an open switch, a closed switch. An open switch means the lights are off. A closed switch means the lights are on. Now, those are not drawn that way in a schematic. In a schematic, we see what we have here on the right, okay, with an open and closed switch. So imagine a wire. Take a wire diagram, just a line, and in that wire, put 2 circles. And those 2 circles indicate a closed switch. Or put a gap in that wire at an angle and put those circles there, and that's your open switch. Okay, closed and open switches indicate whether or not there is flow through the circuit. If there is flow through the circuit, obviously the elements themselves would, I don't know, just consume energy. Okay, they would consume energy. Straightforward so far? Right? Just diagrams, that's all we're doing so far, just looking at diagrams. An electric circuit itself, okay, is defined as something where there's a set of components connected to provide one or more complete paths. One or more complete paths. And we're going to see that in the next section, where sometimes the path that the current takes can vary. So imagine you have wires, right? And then the wire splits. Does the current go this way? Does it go this way? There are ways to determine that using laws. Using primarily like Kirchhoff's laws and Maxwell's laws. We're going to see a bunch of these diagrams in the next section, how to utilize them. So in the next slide, we're going to circuit actually consists of, and by definition, to have a circuit, you need two things: a source of energy and something to use that energy. Without those, you can't actually have a circuit. Now, obviously, they need to be connected, so you need some sort of wiring, but the elements themselves are, again, the source of energy and anything that dissipates or uses that energy. We call that a load-bearing element. The reason being is the idea of a voltage is a load. It says that you bear that load, meaning that, like, you know, the bulb is able to use all of the voltage coming from the power source. That power source is providing all this energy, and then the actual bulb is bearing that load in a sense. It's utilizing that value, that event. All right. But as a definition, a closed circuit is a circuit where the actual charge can move from one terminal to the other. What's the opposite of that, obviously? Yeah, an open circuit. Okay, an open circuit. An open circuit indicates that there's no direct path from one terminal to the other without jumping a space. Algebra 2, have you talked about continuity?
No.
Continuous functions?
No.
Algebra 1?
No.
Good, you did in my class, that's why.
I was freshman year.
Freshman year.
Yeah.
So a continuous function would be something like this.
Oh, we did.
Oh, no, we've done that.
Something that's not continuous might be like this.
Yeah, now I know what you're talking about.
It just does continuity.
Main thing.
Domain restriction. Okay? So an open circuit is a discontinuous function. It's the easy way to think about it. You can't continue along that function without lifting up your pen and starting somewhere else, right? An open circuit, you would follow the flow, open, and then go continuous. You can't. The electrons cannot jump through air to the other part of the circuit. It has to be a closed circuit for this to work. All right. I want to spend a little bit of time now talking about two more things. And this is very heavily. Okay, first I want to take a look at an original incandescent light bulb. These are not the same anymore. Okay, but I'm going over the history of this so you guys have an idea of physically what's happening. So first, I'll point to it so you can see. If somebody wants to just read, please. If somebody just wants to read this. Go ahead, Nat.
Do the letters go with the...
Yeah, but you could just read them one at a time.
A. Current enters the light bulb through the base contact location. B. Charges pass through the filament and are converted to thermal, not all bulbs, and light energy. C. The charges, now at a lower PE, then travel from the filament and back out through the side of the metal socket.
So what we're seeing here, and this is what's interesting, the actual flow starts, it goes into the bulb, goes through the filament, back out. The side of the bulb, ever wonder why it's metal? Because metal conducts electricity. That's why this little, like the threads on the bulb are metal. The metal then touches the side of this casing and exits the actual bulb. In this case, let me look actually a little more carefully. In this case, actually, the electricity enter over here. So let me just show that again. Because I saw A, and I thought it was this wire at first. I looked quick. So the energy is entering here, going into this line. The filament right here is what causes the electrical energy to convert into some sort of photon energy, light energy. It then continues through the filament, goes out the side. When it goes out the side here, the side of this contacts this metal casing here. The metal casing is connected to this white wire right here, which flows out of the bulb. Okay? Now, what's interesting is this. If these two wires, if I continue them, ready? Let's continue these wires. Okay, if these two wires, for some reason, were to, I don't know, fray, and like part of the material started to fray off the side, and this material started to fray the casing that's on it, and for some reason, the wires somehow ended up crossing. Okay, they got twisted up. Here's what the flow is going to do. Think about water flowing down a river. Okay, water's a huge current right down the river. And then there's this big rock in the middle, like a big boulder in the middle of the river. The water doesn't go over the boulder. What does it do? Splits. It goes around, right? It takes the path of
Least resistance.
least resistance. Well, take a look. If I'm electricity and I'm a charge, I don't want to go through this bulb and lose all my energy. So if there's a short in the circuit, this is what a short is, a short circuit. The wires get frayed, the wires touch. The battery down here supplying this, or the outlet, and the energy travels and it says, you know what, I have two options. I can continue into the bulb and lose my energy, or I could say, you know what, I'm going to take this little shortcut and go back in. It takes the shortcut, it's the path of least resistance. When that happens, though, here's what happens. The current keeps traveling through the wire over and over, because it's not going into the bulb anymore, right? The battery keeps supplying more and more current. What happens to the wire? It gets hotter and hotter, hotter and hotter and hotter, until what? Yeah. A fire can easily start from this. That's where you get these electrical fires happening. They're usually starting with a short circuit, or somebody, tampering on purpose so that they can get some insurance payout. But usually it's an accidental short circuit. Okay, you got to be very careful with this. Now, a lot of the time in old houses, in my house that I live in, if I replaced the ceiling unit once, just a simple lamp in the ceiling, or whatever you call it. The wires up in the ceiling in this junction box were so old and like rotting and rusted that I was nervous to even like move them because they were so brittle. Imagine like copper that's been rusted over for years. It's very brittle, right? You can snap the copper in half. The wires were all like that. So we replaced it and it was okay. We put it in the new lamp and it was okay. But what we've been noticing is that a lot of bulbs are shorting out. And one time what happened was I was actually sitting in the room and one of the bulbs like flickered and all of a sudden you heard pop and it literally blew out right there. What happened there was there's a good chance that one of the 4 bulbs didn't get power and too much went to one. And there was too much power into that one bulb, which caused it to kind of explode, the filaments burst. So just be careful when it comes to wiring. You want to make sure that your wiring is new and up to date, and if it's not, you want to run a completely new wire. You don't want to fix wires. You don't want to break the wire and say, I'll attach a new one. You run a completely new wire from your circuit breaker downstairs up to wherever that is in the ceiling. You run through the walls, whatever you have to do, you snake it through usually. So before you take out the old wire, right, you can actually take the new wire, run the new wire up, pull the old wire out, and then pull the new wire through. You can put new wiring in, or else you might get an instance like this. Okay? Okay. Remember we talked about the term load-bearing element? That's what happens here. The charge carriers do not go through the load-bearing element, so there's nothing to bear that load, to take on the voltage. So the wire takes on the voltage, which is why it's getting hotter. But the load-bearing element, when not in place, prevents this system from running properly and it overheats. For today, okay, pretty simple lesson. The last thing for today, terminal voltage. Terminal voltage. So, how many of you have ever used one of these batteries? What do they call them? Okay, but what are they called? That's not the cylinder one. The cylinder ones are, I think, C's and D's, aren't they? There's double A, triple A.
like a square rectangle.
Yeah, what are they called? No one knows? You ever heard these names?
No, I guess.
It's a 9 volt?
Never heard of it.
9 volt battery? It might be called a D cell actually. You know what? You're probably right, Katie. I think it is called the D cell battery. It has some up here. But when I was younger, they called them 9 volt batteries always.
Oh my god. We haven't even done
9 volt, 12. Actually called the D. Oh, maybe not. Just say 9 volt. These ones. But the idea behind these batteries is that it supplies some sort of a voltage. So, for example, this battery itself provides 9 volts of voltage to the actual system. But, unfortunately, what's actually happening is that you're not getting the full 9 volts out. Because the actual inside of the battery has a small internal resistance in it. So that is what's using up some of that voltage right away. So when you get a 9 volt battery, there's usually a small difference between the terminal voltage and the actual voltage supplied. So terminal voltage in this case, okay, the terminal voltage is going to be a little bit less than the actual voltage. So even though this is a 9 volt battery, the terminal voltage supplied to this, not TV for TV, but terminal voltage, might be like 8.9 volts or 8.8 volts. Again, because of this small internal resistance that's occurring inside of the battery. There is some resistance to the battery because of its material itself. Traditionally, we ignore this little thing, right? It's not really much of a deviation. But what we can notice is this. Here's what we notice. This is the important part. Conservation of energy. Conservation of energy tells us that if the terminal voltage is only 8.8 volts, that's what the bulb is receiving. So be careful that when you look at ratings of things, just because the battery is 9 volts doesn't mean that the actual light bulb is getting all 9 volts. So in the lab, not the one next week, but the one after that when we do this, we're going to have a voltmeter. Actually, next week maybe we'll use a voltmeter still. I'll try it. It might work if it's not voltage. And you can take the ends of the voltmeter and put them on the outside of your bulb, and you'll see exactly how much voltage the bulb is receiving. And then you can actually compare that and see how much loss there is to the actual battery. Okay? This section, extremely theoretical. Okay, extremely theoretical this weekend. Okay, but they're all theoretical. There's no math involved. So it's not that long of problems. Okay, please make sure to get to it.